Hello guys, so in this tutorial or video we are going to discuss about optimization technique in machine learning, deep learning or whatever any learning it is in general, and we'll be going through 3 to 4 Streamlit application and one notebook to simply understand what optimization is. So in this one video you will cover all machine learning related optimization thing, and you will have clear understanding what is optimization and how any model approaches or what are the different methods available for optimization. Okay, so after this video you will have a clear understanding of bias variance and optimization, and in the next video you will have a clear understanding of loss function. So you will have a good understanding of how to prepare a model, or how generally all the model behaves, or what are the basic parameters behind designing of any machine learning model. Okay, so as you can see, this is a curvature, right? And this is a curvature, and let's say your initial point in your Google map is this point, and you wanted to reach this deep point, right? This very bottom point of this curvature, right? So how you can reach? You can reach via this path that is smooth. You can reach via this path that is pretty steep, or you can reach via this path. There is multiple ways, right? You can reach this point. So the method, the way you are going to reach from this point to this point is called optimization. So where it requires in any trial and error method, right? Where you don't know the optimal solution and you have to figure out the optimum solution, and that's where your optimization comes. So let's just quickly print about the process, the optimization and stuff. So this picture you have understood, right? Same thing we'll just see. So if you see your loss function for any solvable equation will be like this, right? This U shape, where you, let's say, initialize your initial parameters in somewhere here, and with each step you are coming closer and closer and closer towards your actual solution, which is this point mathematically. So the journey from this point to this point is your optimization technique, right? So you basically optimized your parameter from this random guess to the actual guess. So this is what your optimization method overall. Okay, so yeah, let's just get started with the discussion. So how this method works, basically this optimization algorithm or method, how it works in machine learning. Initially you will do one initialization of the parameters, right? So when your model is initialized, its parameters, that means your biases and weights of your neural networks, are set to some random values, right? And then this parameters determines how the model will make prediction. So the first prediction that the model will guess will be totally wrong, mostly in most of the cases totally wrong, because of this initialization of parameters, right? Because the parameters are not correct. Now in next, what you do with this initialization of parameters, you calculate the loss function. You have the training data, you have the levels or your actual outputs, and you have this random weight values, and then you calculate the difference between your prediction and let's say actual value. So in case of regression, it can be a MSE or MAE. In case of any classification, it can be any binary cross entropy kind of a solution, right? So this loss function will give you the difference between your current solution versus desirable solution. And then once the loss is calculated, you do a gradient calculation, right? So what the gradient calculation is all about, the optimizer needs to know how to adjust the parameters to minimize that loss. So you have some loss value, let's say here you have the loss value of, let's say, 5 or 10. Your target is to reduce it to 0. Let's say it's an case of solvable equation. So the loss function should be ideally 0. So your target is to minimize the value of 10 to 0, right? So your parameters will again readjust so that the equation can be solved. So in graphical term, how you will represent? So in simpler term, it shows the direction and magnitude of change required to reduce the losses, right? So to reduce the losses, in which direction I have to go and in which magnitude I have to go in a vector world, right? And once that is confirmed, then what you will do, you will just update the parameters using that gradient calculation to a newer parameter, right? So your weight will get updated with the gradient calculation, right? So this is your delta L is your gradient of loss. You are multiplying it with some step values, that means your learning rate, and then you are just going in the opposite direction of your previous parameter value, so that your newer value will give you a lesser loss and you are much more closer to the optimum solution. So this is your overall optimization method. Okay, now for the final one is convergence, right? So when you have a zero loss or minimal loss, means with every iteration the loss values are not getting changing in case of non-solvable equations, right? So then you can say that your equation is converged, or whatever loss or problem you are trying to solve using machine learning is converged to the optimum solution. So this is your final step. This fourth step concludes your optimization process, right? So what are the different types of optimization or optimizers you will have? First of all, you will have some gradient enabled optimizers, right? So some gradient descent kind of optimization you will have. So within gradient descent, what kind of optimizers you will have? You will have batch gradient descent, okay, that computes gradient using the entire data set. Then you will have stochastic gradient descent that will compute the weights of any random sample at any step. And then you will have balance between these two, that means a batch gradient descent and a stochastic gradient descent. That will use a mini batch, so it termed as mini batch gradient descent. So in gradient descent you will have these three type of algorithms or basically methods, okay. And then you will also have momentums and adaptive optimizers, right? So we'll also discuss about them. So till now within gradient anyone, I don't think, have any question. So gradient based approach is pretty simple, right? So let me just quickly go to this application that we have built, right? So how, what we are talking about, we are talking about SGDs, right? So if you see how SGD works or stochastic gradient descent works, that it updates weights using a single random or mini batch. So in case of mini batch, it terms as mini batch gradient descent, right? It leads to faster but noisier updates, right? So here if I go to the code, right, and if I go to the methods code, you will see, so we have a problem or a loss function, okay, and we use this different momentum or some gradient based or some adaptive technology based solutions, and we'll discuss one by one about everything. And this is the loss function, okay. So the loss function is mostly quadratic and some sinusoidal solution is also there, okay. So you can see this is the loss function. So we'll go one by one the solution and code as well, okay. So you can see this is the solution in front end, how it looks like. So what we have some drop down here where I can choose the number of optimizers based on my choice, and there is one slider where I can fix the learning rate, and I have two plots, one 2D plots with optimization path and one 3D plots with optimization path. So here you can easily clearly understand the optimization via 2D plot or a line chart as well as a curvature chart, okay. So in code also how we'll understand, you can see after the necessary imports, here we have all the necessary imports. So for selection, this select box is basically what we are using here. So whatever we are selecting, okay, all this drop down, and we have given the options, okay. And this, once you select something, the same explanation comes here from this dictionary, okay. And once that is done, the slider details we have coded here, these are the slider details, okay. and there are some fixed values also. So let's say I choose momentum, that we will see. Now you will see another momentum slider came, right? So let for now, for the time being, let's keep concentrate on SGD, as we're just discussing about gradient algorithms. And then once that is done, based on the loss function calculation, okay, how it will converge, that we are going to decide, and the same thing we are plotting here, right, how it is converging. So let's increase the learning rate, let's say, and let's see how it changes. Okay, in 2D, it will be much more understandable. So if you see now, if you increase the learning rate to 0.08 for this function, loss function, you will have the global optima with the predefined sets of x and y's, right, the optimization path, and how accurately it is reducing the noise, or basically loss function, right. And here in the 3D graph you can also see the same, right. So let's say if I now increase it to 0.09, I can see the values of different steps, correct step counts. Here also, as it's a 3D plot, it will take some time. You can see, right, how your loss function changes with how your optimization steps are getting changed with loss function, right. So this is the overall loss function with SGD. So gradient is the most simplest optimization method I can see. So I can tell you right now, you also have this momentum, then adaptive, then you also have two second order optimization methods, where right now it is only using gradient, that means first derivative of the loss function, but there they uses I forgot the name of the matrix. I'll tell you in a while, but there they uses first order as well as second order derivatives, so that they can use the curvature, okay, the curvature information of the surface to reach the global minima. So they can easily escape the local minimas if you use the curvature information, right. Okay, now let's moving ahead. You have now momentum also, right. So in what momentum based optimizers, okay, what they use, this method helps accelerate the gradient descent by using momentum. So I hope you all are aware what is momentum. Okay, momentum is nothing but if in case of physics, it's mass times velocity, right, so mv. So what it is doing, it is using the information of gradient as well as the uh, it accelerates the gradient descent algorithm by using momentum. So that if the basically, let's say this optimization method, right, so here you can see, if you reduce for SGD, if you reduce the learning rate, you can see it will stuck here, right, it will stuck in the local minima, but it requires the correct learning rate, right, so that it can reaches. Now if you increase further, okay, so you see it is reaching the correct value normally. Okay, so to help this SGD, you are introducing momentum, where they are just accelerating this method, so that it does not stuck in local minima. And how they are accelerating this process, by using momentum. Okay, so you have to remember this momentum based algorithm. Okay, so what it does, it adds a fraction of previous update to the current update. So whatever previously we have updated, it adds the fraction, basically alpha times or beta times, whatever, right, it's a fraction of update is being carried over and added to the next update. Okay, so that it does not stuck and have some momentum, and it helps in avoiding the local minima and speeding up the training process, right. So if you add the previous update to your current update, what it will happen, it will definitely speed up the process, right. Now the next one is adaptive based learning optimization, right. So we have already learned two type of optimization, one is your momentum and one is your gradient, right. The third one is adaptive based. So what it does, it adjusts your learning rates, okay, based on gradient information. So the second one is adjusting the learning based on your momentum, or basically accelerating your learning or gradient based on using information from momentum. And the third one is adjusting your learning rate. That means this learning rate they will adjust automatically with the help of gradient. Okay, and in this category of adaptive learning rates you will have AdaGrad, RMSprop, Adam, AdamX, NADM, this kind of optimizers, right? Mostly that we are using in deep learning. So we'll see that one also, but let me just quickly wanted to configure another type of optimizers here, that is your second order optimizers. So in case of second order optimization methods, we'll have Newton's method and BFGS or LBFGS. These 2 to 3 methods we have, and we are going to use this kind of optimization not practically in research they are using, where high accuracy of any solution is required. Okay, so what it happens, it also considers not, it does not only consider the gradients, but it also considers the second order derivatives basically. So right now in all these functions, right, whatever you are doing d dx of the loss function or d dy of the loss function, right? But here they are considering d dx of the loss function, d dy of the loss function, d square x dx square, d square y dx square, d square l dx dy. That means all the second order derivatives also they are considering. So what it will give, if you do second order derivative of any curvature, it will give you the curvature information as well, right? So if you have the curvature information, it will be pretty much easier for any equation to get converge much faster, right? So this is what your second order optimization. But from as when you are going to use second order derivatives, right, it should be a very computationally expensive. So practically in any deep learning methods basically this is irrelevant, and nobody normally uses the second order approaches. So we have Newton's method, we have LBFGS. So I don't know the full form of BFGS method basically, but these are kind of a quasi Newton's method kind of a solution. Okay, so one quick thing that you can remember here, that what optimizer is right for your problem. So for large data set you can choose Adam or RMSprop. For small data set you can go with SGD with momentum. For non-stationarity data you can go with RMSprop again. Non-stationarity data you can definitely go with RMSprop or let's say Adam. For sparse data you can go with AdaGrad. So these are the details that I wanted to share. Okay, so yeah, now let's again come back here. So here you can see one small examples that I have created in TensorFlow. So what we are doing here is that we are just importing TensorFlow, then we are just doing a data load of MNIST data. So you can see kres.dataset.mnis.load data. This method will give me all the training and testing dataset. Now once you have the MNIST dataset, you are just dividing all the pixels by 255 at its 0 to 255 grayscale pixel. So that means only black and white. So these examples we have also done in the TensorFlow tutorials. You haven't watched, you can go and watch and have a good understanding about all of these codes. So once your data set is ready, that means normalized basically, then you are calling a sequential deep neural network. It's only for example purpose of this optimization technique, right? So then you're just using building one neural network. Okay, you can use model.summary or you can print the structure of the model. It's a simple neural network. In optimizers dictionary here I have defined all the required optimizer that I am going to use for this tutorial. So you can see here we are using SGD, momentum, adaptive methods like Adam, AdaGrad, NADM, RMSprop, and finally we are calling this model.compile to compile with all these optimizers one by one. We are using sparse categorical cross entropy for loss function, and to optimize it on based on accuracy we are providing the matrix as accuracy. Okay, and then we are calling the model.fit method to train the model, and we are passing the batch size as 32, and we are printing the accuracy and loss function here, and we are repeating it for 3 iterations per optimizer. So here you can see the first training will be definitely, it will go according to the list order. So first it is training with SGD, then it is training with momentum optimizer, then it is training with RMSprop, then it is training with Adam, and then it is training with Adagrad, then it is training with Nadam, right? So these are the different optimizers, and these are their accuracy and loss values after third iteration. So that's a simple TensorFlow example, and in the next block of codes we have done the same with torch. So PyTorch, same MNIST data you have loaded using data loader in PyTorch. Once that is done, you have created again one same feed forward neural network. Okay, once the neural network is done, so you have defined the loss function here and initialization of the model. Once that is done, the same thing you have repeated for all the 6 optimizers, and you can see the code here, and you can see the output that training with SGD started, training with SGD finished. Here we haven't printed the stepwise loss or final loss or accuracy with the optimizers, right? So this is in the notebook basic example how to use optimizers in your high level, because normally in deep level, if you does not have very classified problem, you are not going to write yourself optimizers. That means you are not going to play with the parameters yourself, and you are normally going to use the default ones that is set there, right? So that's it for this notebook basically. Now we'll just see, if you see the methods, right, we have this 2D some sinusoidal and parabolic equation that we're trying to solve using the x and y values and using these methods, right? So where we have said that we have already shown the example using SGD. Now if you change let's say SGD to some momentum, so momentum, what it use, it accelerates the SGD using some momentum value, right? So that it converges faster, it does not close in your local minima basically, right? That's what we have learned. So if now I reduce the learning rate where it is stuck to the local minima, right? But when you are using some momentum, see, it is not getting stuck here, it is coming much more deeper. Okay, in surface wise also it is coming here, so it is not stuck in here, right? So if I reduce the momentum a little bit, so I will see it's slowly coming off, right? It's slowly speeding the process, and it is coming from this position to this position. So in SGD, right, if your SGD with 0.3, if you see, right, so if you have SGD with 0.3, it is stuck here, right? But if you go to momentum with same learning rate 0.03, and if you limit the momentum to let's say 0.4, you will see that it has already converged, right? It has already converged. So a little bit help of momentum pushes the SGD algorithm to converge much more faster. So that's why momentum works much more better than SGD when you have local minimas, and in any normal real-time examples you will have local minimas. Okay, and the same thing you can see in the 3D optimization plots. Okay, now let's go on to the adaptive ones. See, this one is RMSprop. So RMSprop adjusts the learning rate dynamically based on the magnitude of the descent gradients, preventing large updates and improving stability. Can you see the same thing happening here? Okay, so what it is saying that RMSprop adjusts the learning rate dynamically based on the magnitude of the descent gradient. Okay, so what is the magnitude of descent gradient? Based on that value, it is preventing large updates, and it is mostly used for stability. So if I now increase the learning rate, okay, so you can see all the updates at the very last, right? It mostly in a stable position. Okay, why it is happening? Because it uses the last learning rate dynamically basically to adjust your learning rate. So now if I increase the learning rate again, I will see it got converges, right? So that's how. So in case of momentum, you see, right, with 0.3 but momentum around 0.44 value, this equation got converged, right? So that's why I am saying that RMSprop will be a best solution for your non-stationarity data problems. Okay, so in that cases you can use RMSprop. Now the next one is here is Adam. Okay, so Adam combines the momentum and RMSprop, adapting learning rates per parameter for efficient training. So it should be computationally expensive because it has more parameters, right? So what it is doing, it is combining the knowledge of momentum as well as RMSprop. That means it is using RMSprop means what? Your gradient information as well as momentum values, right? So here you can see again, if you adjust these beta values, you can see the convergence will be much more faster. Okay, so as you can see, okay, so let me just reduce this beta 2 for convergence, see in which value it get converges, that's important. So I just increase the learning rate to 0.8 and beta, so you can see if around 0.1 learning rate, I think it should converge, right? Yeah, near about convergence. Let's just do it 0.1 and increase the beta 1 value a little bit, and this beta 2 as well. Let's reduce the beta 2. So here you can see it's mostly converges, but see the steps, learning steps right here. So it uses momentum and RMSprop, so and it uses it adapts the learning rate per parameter. So that's how you can tell that this Adam works. And in 3D also you can see the same graph. I'll ping you all the codes, right, so that you can play along with. Now comes to AdaGrad. So what AdaGrad does, that it scales learning rate based on past gradient, making it good for sparse data but leading to vanishing small learning rate over time. Okay, so it has a vanishing gradient problem, but it is normally, you know, scales the learning rate based on past gradient. Okay, based on past gradient values, it scales the learning rate. So if I initiate the learning rate to 0.05, it then what it will do, it will scale the learning rate values based on the past gradients. Okay, so it is good for sparse data, but it is again there also it leads to some vanishing gradient problem. So that's your AdaGrad. Okay, and the final one is NADAM. Okay, it's a combination of Adam and Nesterov momentum, providing improved convergence speed. So the convergence speed got improved with this method. So if I just increase it to 0.9 and adjust this beta 1 and beta 2, I will see some good convergence here mostly, right? So it uses Adam and Nesterov momentum. Okay, and same thing you can see in the 3D plots. I'm not showing the 3D plots much, right? So as I have very less amount of time and much more things to cover here. Now let's go to the second one where you will see the same kind of a loss function. Now this is the second one, right? Now the second one is this optimization, right? So here also you will see this is a loss function where again you are using some sine solution as well as some parabolic equation. Okay, so it's a parabola and some sinusoidal values. Okay, so this is your loss function basically. Let me just quickly initiate again. And here what is the purpose of this application basically? So you can see by changing all of these left parameters that's readily available for your optimizers hyperparameters basically. So how you changing these values, how your iteration and parameter values will look over time, right? So now let's say if I increase the learning rate to 0.1, okay, you can see how your gradient descent values, okay, got converged, or how your gradient descent values change over iteration. Now if I increase the iteration to let's say 100 for this loss function basically, so you can see how these values are converging around this 4, right? Now let's say you are increasing beta value for your momentum solutions, so you can see your momentum values or this one is your RMSprop. So RMSprop does not use momentum, right? It's adaptive methods, and the gradient descent momentum and RMSprop and all these values optimize the trajectories you can see, and this is the optimization problem. Okay, so you can play along with this also. So you can also change the Adams beta 1 beta 2. So here also, here we have seen, right, what is basically Adam is nothing but combination of two things, right? So Adam is a combination of momentum solutions and RMSprop solution. That's why you will have two betas, right? Beta 1 and beta 2. So here also you have beta 2 and beta 1, and then in RMSprop you will have this epsilon just to avoid zero divisional errors and all, and this is Adams epsilon. Okay, and here also you will have the equation. So gradient descent is nothing but updating the weights based on the gradient. So this is your loss functions derivative, this is your learning rate, and you're just subtracting it with the older values, and you are getting the gradient. Okay, and you are getting the newer values for gradient descent. For momentum also, what it is doing, it is adding momentum, right? And it is fraction of previous basically updates it is taking, and once the previous update is done, okay, it is taking the current gradient basically. So once it calculates all of this, it is considered as momentum. So once the momentum is calculated, then you are getting the final. So your beta is termed as momentum coefficient, you are getting your final output here. RMSprop, similar way for non-stationary solutions, you can see your decay factors and your divisional error. I mean, how it's just for computational purpose, so that your denominator becomes 0, this solution will become invalid, right? So that it does not happen, that's why they added a epsilon here for RMSprop. And Adam, you can see it's a mixture of this momentum and RMSprop basically, right? So this is the optimizers equations, and these are their trajectories. It's only following these equations based on this hyperparameter, so you can play along with it and understand how your optimizers will change values. Okay, so that you can have a good understanding of for which solution which optimizers needs to pick. And this is, I think, one TensorFlow example basically. So we have seen two methods here. So this is the third method, where I think it's a TensorFlow optimization problem. Okay, where again similar kind of thing. If you choose the neural networks, let me close all of this too, because it's already done. I've shown you the process. Okay, so here also you can choose any of the optimizers. Let's say I'm going to choose Adam, I'm going to choose a learning rate of 0.2, and if I do a training on top of the model, so what this application will show me, this application will give me the number of epochs. Let's say I'm just going to train for 2 epochs, batch size will be 32, let's just increase it to 128, and let's just train the model, and let's just wait for output. It will give me the training and testing accuracies in a plot. Okay, so yeah, this tweakings you can do, and you can easily see how your losses varies with epochs, how your accuracy over epochs based on the variation of your optimizers, and then you can choose the perfect optimizers based on this. Okay, so this example tells about that one. So here in the code, if you come, computer is hanging for just give me a second. Okay, so here same we are loading the MNIST data, then we are doing the same normalization, we are building some we are flattening out the data, then we are doing one dense neural of 128, then a dense of 10 for classification problem. Similar kind of thing, we are doing one slider with the learning rates to be varied. We are having this additional hyperparameters fixed to be 0.9, 0.9, 0.999, and we are again doing sliders. If you are choosing momentum, we are giving you the momentum values to be configured. If you are choosing to be Adam or Nadam, we are giving you the beta 1 and beta 2 coefficients in the equation that we have already seen to be configured. Once you configure all of this, we have this dictionary For SGD, momentum, RMSprop, add a grade and Adam, and once that is ready, again in another slider you will have the number of epochs you wanted to train, number of batch size you wanted to train for every iteration, and then with every output, when you are clicking on the submit, it will just create the it will just train the model. Once the model is trained, the output will you are getting as plots here, right? So if I just increase the number of epochs here, okay, now let's I'm just changing it to momentum, okay, and I'm just, let's say, doing a batch size of 48, and let's say just I'm just training the model. So once the training is done, I will see a progress bar here, okay. So let's just wait the training to be finished, and once the training is finished, I will have the plots. So here you can see the losses are getting decreased over epochs. The validation loss is also getting decreased, and the training loss is decreasing drastically. So it indicates that with this set of training, my model is basically kind of you know what it is, underfitting or overfitting. You tell me. Your training accuracy is 93% or 94%, your validation accuracy is 86%. That means it is performing good on the training dataset but bad on the validation dataset. That means it is trying to overfit, okay. It's a overfitting problem. So we have to solve so how you can solve overfitting problem, you can go and watch the previous video of the bias and variance and then come here, right? So that also you can see. So and here you can see the accuracy, how accuracy got increased over epochs per epochs. So that's a simple application again we have built, and you can play along with the optimizers details. And the final one is, so this one also I have built, but it has some issues. So it also shows how second order optimizer works. So here also you can see for one model you can choose any of these first order derivative optimizers, and here I have only kept this LBFGS, this second order optimizer. I'll make another video regarding only the second order optimizers, but later, only when we will become much more proficient, right, with machine learning and all in the video series. I think after 30 to 40 videos I'll make one video for this. And here you can again choose the learning rates, beta value, coefficients, number of epochs, and you can train, and it will show you the error and accuracies again with the problem. But currently it is not supporting because some issues I haven't debugged. It's some PyTorch issue. But anyways, let's go on, and this is the final one example, a real life use case example. Let's say we are trying to do some optimization based on some trading return strategies. So let's say you have some stocks of Apple stocks for some time period, okay. These are the values of your Apple stock, and let's say I'm going to choose momentum optimizer, okay. So in momentum optimizers I'll have a learning rate and momentum values that I have configured here, right? And I have this Apple stocks value for some 2023 to 2024 1 year data on a day basis, okay. Now I have some short term moving average selection, and I have some, that's a long term moving average selection. Based on that I'll have some return values here, okay. So this is the return values. I can see for February how the return got increased, for April, for August how it got decreased again. So this is the based on the data, okay, based on the data set how Apple performs, okay, return wise. And this is another curve of your strategic return, okay. It uses some formula to calculate the strategic returns, and then after when you've done the optimization of the strategy parameters, okay, some algorithms you write based on this momentum optimizer, okay. You do some optimization, and this is your final optimized strategy performance, you can see, right? So here based on the date you can see this blue line indicates your optimized strategy returns, and here you can see the market returns. So market return is currently better than the strategic optimization returns, because definitely, right, this, if you see this optimization path, this is nothing but a straight line. So it is the loss is not getting decreased over time, right, because of this less number of data basically, okay. So same thing, if you change it to Adam, you will have to adjust this beta 1 beta 2, and you can play along with it, Okay, and you can see how your final optimized graph got changed for your optimized salary strategy. Okay, so you can see how your graph changed here. So in code, let me just quickly show you how we have built this trading application for optimized strategy. Okay, so we have used Yahoo Finance for this. Okay, so here you can see we have Yahoo Finance. We have used same 6 set of optimization method. Okay, same thing, we have this hyperparameters, we have tuned as in sliders like the previous ones. Okay, if you are coming from the previous videos you have seen. So we have downloaded the data, and once we have chosen or downloaded the data, right, we are calculating the returns based on the percentage change of the close column. Okay, and then we are plotting the close column first, okay, in a line chart. So if you see, the first chart is nothing but your Apple stock value, okay, in line chart. Okay, now the next one is we are defining one short window and one long window, okay, for moving average crossover. Okay, so let's say normally in trading, what happens, you choose a 20 slider and a 50 slider. Okay, so this is a basic 20 and 50 moving average. If they cross one another, so it turns out that the stock particularly becomes bearish or bullish. Okay, so the same strategy we have used here. So strategic return, okay, you can see the code for strategic return is nothing but, okay, we are picking up the signal, and then we are just doing a shift, and then we are multiplying it with the return value to calculate the strategic return. Okay, and then we are plotting the returns and strategic returns. So you can see the first plot is your return plot, and the second one is your strategic return plot. Okay, and finally, when you are performing this optimization, so here you can see you have the training loss defined, how your loss will look like here. Okay, long based on long and short. So this is the equation. Basically, this loss column parameters we are trying to optimize based on all the optimizers there, and this is the optimization method we are using. So we are initializing the parameters, then again we have this 6 set of optimizers, and then we are just running the optimizers, right, for optimizing this loss function. And once we have completing that, we are just plotting the performance of the optimizers. Okay, and we are plotting that, okay, what is my short window, what is my long window, and then based on these values we are just plotting the optimized strategic return and what is my normal strategic return, right. So this is my market return, and this is my strategic return, optimized strategic return versus market return. So likewise you can also plot the strategic return and optimized strategic return, and see if there is any improvement or not based on the optimization. And you can definitely increase this. So in most of the non-stationary database, RMSprop works well. So this is one practical use case that you can also add in your school project, a college project, or in your resume, and you can explain your employer how you have understood optimization techniques with the help of this code as well. So yeah, that's it for this video. I hope you have if you have watched till this far, I hope you have liked and enjoyed and have gained some understanding regarding optimization methods, how optimization works. So I'll hope you all the best in your machine learning journey, and we'll meet you soon. Thank you very much.